Good morning, class. In this lecture session, we'll start dealing with terminated transmission lines, and therefore we look at the concept of impedance seen by the seen by the source, and then we'll look at the reflection coefficient when the line is terminated in a load that is different from the characteristic impedance. Thank you. In our earlier slides, we'd shown from equations in equations 12 and 13 that for a transmission line injected with a voltage V and of course having a current I, the solutions for the line voltage and current are given in equations 12 and 13, where gamma is the propagation constant of the line. Now, further, the current is related to the voltage through equations 7 and 8, which we of course repeat here. So your I of Z is equal to minus 1 over R plus J omega L dV over dZ. And of course, dV over dZ, when we differentiate dV with respect to dZ, we get gamma over R plus J omega L, V1 e to the minus gamma Z, minus V2 e to the gamma Z. Now, R plus J omega L over gamma is equal to Z naught. Therefore, our I of Z is 1 over Z naught into V1 e to the minus gamma Z minus V2 e to the gamma Z. And therefore, IZ times Z naught is given by equation 37, multiply both sides by Z naught. Now, at the input, where we've injected our source, at Z equal to 0, we have our current is given by I naught, which is 1 over Z naught, V1 minus V2, as given in equation 38a. And the voltage at that particular input, which is V naught, is given by V1 plus V2, as shown in equation 38b. Let's consider transmission line of total length L, characterized by a propagation constant gamma, which remember is a line secondary constant, and also characteristic impedance Z naught, which is also a secondary constant of the transmission line. And we terminate this particular line in load ZL. Now, of course, at the load, the current is IL and the voltage is VL, that is at Z equal to L. Now, the line is fed by a generator of input impedance ZG and open circuit voltage VG, as you see from at Z equal to 0. So, our transmission line, being of length L, extends from Z equal to 0 to Z equal to L, which is at the load. Now, to determine V1 and V2 from the equations, the terminal conditions must be given at Z equal to 0 and Z equal to L, as stated in equations 38a and 38b. Remember, in this case, Z is equal to 0. Therefore, we get I naught and V naught. Now, substituting these terminal values, which are generally measurable, we can only place our instruments at either ends, at the generator or at the load. So at Z equal to 0, we substitute for V1 and V2 as follows. We know that our I naught is 1 over Z naught into V1 minus V2. And therefore, V1 minus V2 is equal to I naught Z naught. That's in equation 39a. And similarly, V naught is equal to V1 plus V2 at 39b. Remember, your Z is equal to 0 at this point. Now, if you add and subtract those two equations, 39a and 39b, you find that 2V1, when you add, 2V1 is equal to V naught plus I naught Z naught, and therefore V1 is a half into V naught plus I naught Z naught. That's equation 40a. Similarly, if you subtract 39a from 39b, then you get 2V2 is equal to V naught minus I naught Z naught, and that implies that V2 is equal to a half V naught minus I naught Z naught. That's equation 40b. So these are important equations. We have V1 and V2 determined in terms of measurable parameters, I naught, V naught, and Z naught. Now, if the input impedance at the input terminals is Zin, then the input voltage V0 and the input current are easily obtained from basic circuit theory. So V0 is equal to Z input over Zg plus Z input times Vg, where Vg is the open circuit voltage of the source. That's equation 41a. And of course I0 is Vg over Zg plus Zin, because that's the total impedance seen by the source. That's equation 41b. On the other hand, if we only have access to the load ZL, and this tends to be quite the reality, when, for example, you are installing an antenna on a tower, you can only access the voltage or the power at the antenna side and the reflection coefficient at the antenna side. You don't have access to the generator because that tends to be restricted. And therefore, if we have access to VL, which means that is the current, we have current to the load, so our Z there is equal to L, and therefore I of Z at Z equal to L is I subscript L, and V of Z at Z equal to L is V subscript L, as shown in equation 42. And therefore, our VL is given by 43a, and our IL times Z0 is given by equation 43b. And therefore, if we again add and subtract equations 43a and 43b, we find that 2v1 e to the minus vl, that is when we add, is given by vl plus il z0, and therefore we get v1 in terms of vl, il, and z0. Now also 2v2 e to the gamma L is equal to VL minus IL Z0 if you subtract that. So our V2 is given by equation 44a. Therefore, our two constants in the line, V1 and V2, are given in terms of measurable quantities, VL, IL, Z0, and of course the total length is known, and the primary parameter, the secondary parameter, gamma, is known. Now thus the input impedance seen at the generator Zin is determined as follows. Now your Zin is simply the ratio of V0 over I0 if you look at the transmission line. Now of course we have V0 given by V1 plus V2, and then I0 is 1 over Z0 into V1 minus V2, so you have equation 45. Now our V1 and V2 are given by the terminal voltages and current, that is IL, VL, and that is how we get equation number 46. We replace V1 and V2 with what we had in equation 44, and therefore we get Zin. However, we also know that ZL is VL over IL, and therefore we have Zin, that is, you divide everything in equation number 46 by IL, and therefore you have Zin in terms of Z0, ZL, and e to the gamma L and e to the minus gamma L. And of course, when you assemble these terms, you end up with equation 47, where what we have, hyperbolic tangent gamma L, is given by e to the gamma L minus e to the minus gamma L between brackets over, between brackets, e to the gamma L plus e to the minus gamma L. That's the definition of a hyperbolic tangent. So this is the input impedance, that's equation 47, seen by the generator for a line of length L terminated in an impedance ZL. That is a very general expression for that transmission line. Now let's consider three special cases. In the first case, let's consider a lossless line where gamma is equal to J beta, since alpha is equal to 0. Therefore, the input impedance Zin is given by that expression. We have tan gamma L now being replaced by, hyperbolic tangent gamma L being replaced by hyperbolic tangent J beta L. Now, we have to determine hyperbolic tangent J beta L. Now, hyperbolic tangent of x is given by e to the x minus e to the minus x over, between brackets, e to the x plus e to the minus x. Now, if you replace x with jx, then you have the second expression there. But we know that e to the jx from trigonometric identity is simply cos x plus j sine x, while e to the minus jx is equal to x, cos x minus j sine x. So hyperbolic tangent jx is then expanded, and we get from equation 48, it's given by 2j sine x over 2 cos x, which is equal to j tangent of x, which means hyperbolic tangent of jx is simply j tan x. So it means that in the above expression, where we have hyperbolic tangent of j beta L, we'll replace that by j normal tangent of beta L. And that is what we get in equation 49. So for a lossless line, your input impedance is equal to Z0 into numerator we have ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. So this is the expression for the input impedance for a lossless line. Now, in most practical cases, the transmission line has low loss. For example, feeder cables for antennas have fairly low loss. Hence, equation 49 is a good approximation for the input impedance for a short low loss line. So it can always be utilized. Now let's consider an open circuit line which is lossless, which means ZL is infinitely large. So our input impedance as ZL goes to infinity is given by Z0 into ZL over JZL plus tan beta L. Remember, we've decided to neglect any term that doesn't have ZL because they will be small, and therefore Zin, which is Z open circuit, is equal to minus J Z0 cotangent of beta L, as shown in equation 50 for an open circuit line. On the other hand, for a short circuit lossless line, ZL is infinitely small, which means it's going to 0. Hence, again, Zin, when we neglect anything to do with ZL compared to Z0, we end up with Zin being given by Z short circuit, which is J Z0 tan beta L, as shown in equation 51. Now, if you take the product of equation 51 and 50, you have Z open circuit times Z short circuit. The two J's give you, when you multiply them, they give you minus 1, and multiply by a negative sign in 50, that is plus. Then you have two Z0s, which means we have Z0 squared, and then you have cotangent of beta L times tangent of beta L, which is 1. And therefore it means that Z open circuit times Z short circuit is Z0 squared, and therefore the characteristic impedance of the line can be obtained from equation 52, which means if you know the open circuit input impedance and you have the short circuit input impedance, then you can get the characteristic impedance of the line using equation 52. Now finally, let's assume that the load is terminated in characteristic impedance, which means ZL is equal to Z0. Then when we insert this into our equation, we find that the numerator is equal to the denominator, and therefore Zin is equal to Z0 when ZL is equal to Z0. Thank you. Now, as we've seen before, for a typical transmission line, you have a forward traveling wave and a reverse traveling wave. Now, we define the reflection coefficient as the ratio of V2 over V1, which means the reflected wave over the incident wave. Now V2 we've seen before as given by 1/2 between brackets VL minus IL Z0 e to the minus gamma L, while V1 is 1/2 into VL plus IL Z0 e to the plus gamma L. And therefore, when you look at this ratio, you end up with the equation for 55, where gamma at a distance L from the load is given by ZL minus Z0 over ZL plus Z0 e to the minus 2 gamma L. Now at the load, your gamma is gamma L, and therefore your L there is 0, and that gives us equation 56. The reflection coefficient at the load is ZL minus Z0 over ZL plus Z0. A very important expression. Now, let's derive the reflection coefficient in a slightly different way. Just consider this particular line where we have point A at the input, and that's where we inject our incident wave. And at point B, which is a distance L from point A, we have our load ZL, and we extend this from point B to point C, another distance L. So if you consider the above transmission line, assume the line has characteristic impedance Z0, and it is terminated at load impedance B. If you have that incident wave V1 traveling from terminal A towards terminal B, the incident voltage at B, the wave having traveled a distance of L, is given by V1 e to the minus gamma L, where gamma is the line's propagation constant. Now, if there was no termination at B, then the incident wave at terminal C, a further distance L from B or 2L from A, would be given by V1 e to the minus 2 gamma L. Now at B, a portion of the incident wave will be reflected, resulting in a reflected wave V2. Remember, we have termination at point B. The wave will be traveling backwards towards the source, terminal A, where the reflected wave becomes V2 e to the minus gamma L. Remember, it has traveled a distance of L from B to A. Now if we assume a reflection coefficient gamma L at the load, then V2 is simply gamma L V1 e to the minus gamma L, where of course V1 e to the minus gamma L is the incident wave at point B. So that at terminal A, the reflected wave becomes V2 e to the minus gamma L, which is equal to gamma L V1 e to the minus 2 gamma L. Hence, the ratio of the reflected to the incident wave at terminal A becomes gamma L, small l that is given by gamma capital L, that is the load reflection coefficient, e to the minus 2 gamma L. So that is equation 57, where of course gamma L is given by ZL minus Z0 over ZL plus Z0. Now let's also consider an alternative expression for the input impedance in terms of the reflection coefficient. Now we have the general expression which we have derived for the input impedance, the impedance at the input of a transmission line terminated in the load ZL. We have that. Then we replace the hyperbolic tangent of gamma L in terms of its definition, which is e to the gamma L minus e to the minus gamma L over e to the gamma L plus e to the minus gamma L. So we do that in both the numerator and denominator. Then we multiply both numerator and denominator by e to the gamma L plus e to the minus gamma L. Then we collect terms of ZL plus Z0 and ZL minus Z0 in both cases. Then we divide both denominator and numerator by ZL plus Z0. And when we do that, we end up with the expression number 58, where Z in is equal to Z naught into the numerator 1 plus e to the minus 2 gamma L, capital gamma L, over 1 minus e to the minus 2 gamma L, capital gamma L. So that is the alternative expression for the input impedance seen by the source in terms of the reflection coefficient along the line of length L. We'll next take two examples. These are in tutorial sheet number 2. Of course, we are asked to use the Smith chart, but we can only use the Smith chart next week when we have covered it and we have derived it. Now let's look at example 1, where a 70 ohm lossless line has a standing wave ratio of 1.6 and an angle of the reflection coefficient phi is equal to 300 degrees. Now if the line is 0.6 wavelengths long, you are supposed to obtain the reflection coefficient, the load impedance, the input impedance, and the distance of the first voltage minimum from the load. Now, we'll not solve equation 4, but we can use the tools at our disposal now to solve for parts 1, 2, and 3. So VSWR is simply given by 1 plus magnitude of reflection coefficient over 1 minus magnitude of reflection coefficient. We'll cover this tomorrow, which implies that the reflection coefficient, the magnitude of the reflection coefficient is simply 1.6 minus 1 over 1.6 plus 1, which is 0.2308. And therefore, our reflection coefficient gamma is the magnitude and the phase angle. The phase angle is given as 300 degrees, and therefore 0.2308 angle 300 degrees. Now, our gamma L is gamma naught, which is ZL minus Z naught over ZL plus Z naught. So our ZL is given by Z naught into 1 plus gamma naught over 1 minus gamma naught, which is gamma L. And therefore, from that expression, knowing the values of gamma naught and Z naught, we find that our ZL is 80.6 minus J34 ohms. Now the input impedance, you have the standard expression there, but we have to get our beta. Our beta is 2 pi over 2 pi over lambda, and the length of the line is 0.6 lambda. So it means that our beta L is equal to 1.2 pi, and therefore tan beta L is 0.7265. Now our Z in, therefore, just insert the values of tan beta L, Z naught, ZL into that expression, and when you solve it, you find that your Z in is 48.68 minus J 17.61. Now we'll solve the same problem using the Smith chart in sometime next week, and we expect that we should be able to get an answer close enough to that. Finally, we have example number 2. You have a 30-meter long lossless line with Z naught given by 50 ohms, operating at a frequency of 2 megahertz, and is terminated on a load ZL is equal to 60 plus J40. Now, if the phase velocity is given by 0.6 c on the line, you are supposed to use the Smith chart. Of course, we will not use the Smith chart here. You are supposed to determine the reflection coefficient, the standing wave ratio, and the input impedance. So again, the solution is similar to what we had before. Our gamma L is ZL minus Z naught over ZL plus Z naught. Remember, we call it gamma L, sometimes we call it gamma naught. It's the same thing here. So our gamma L in this case is given by 0.352 with an angle of 56 degrees. Just remember, gamma L is a complex number. It has a magnitude and it has a phase angle. And one thing about gamma L, or gamma in general, is that it is never greater than 1. So we can only get a magnitude of gamma L, or gamma in general, that is less or equal to 1. Now we will use that fact to derive the Smith chart. Now to get the standing wave ratio, Normally, sometimes we call it VSWR, sometimes just SWR, because the current standing wave ratio would be similar. So the standing wave ratio is 1 plus magnitude of gamma L over 1 minus magnitude of gamma L. And of course, the magnitude of gamma L is 0.352. When we insert that, we find that our standing wave ratio is 2.09, which is approximately equal to 2.1. Now, to get the input impedance, we have to get our beta. Now, our beta by definition is omega over phase velocity. Now, our omega is 2 pi times 2 times 10 to the 6 over phase velocity is 0.6 of c, and therefore phase velocity, our beta is 0.0698 radians per meter. Of course, we can also get the guide wavelength, which is 2 pi over beta, and it's 90 meters. Now, you should be able to observe that the guide wavelength and the free space wavelength are different. Now, therefore, our tan beta L is simply the tangent of 0.0693 times 30, and of course, 30 times beta, L times beta is in radians. We can change that to degrees, which is 120 degrees, and therefore tangent of beta L is equal to minus 1.7336. Now, when we insert this into our general expression for Zin, we end up with Zin being given by 24 plus J 1.4 ohms. Thank you so much, class.